So welcome to CSC 241, and we are picking up where we left off on Friday. What you see before you is a simple truth table that reflects the possible input combinations for the AND operator, whether a Boolean operator or a logic gate, whether we're dealing with a software operator or a hardware logic gate. We have this set of outcomes. I want you to notice the pattern here. Half in the leftmost column, the first half of the values are 0 or false. The last half of the values are 0 or false. And then as you move in columns to the right, they alternate more frequently. There's only 2 columns here, so we have 0, 1, 0, 1. Is there anyone else that would care to offer a plain observation about the outputs for AND? Is there anyone who would volunteer to offer an observation about AND?
As long as one of the variables being calculated are 0, the output's always going to be 0.
That is correct. That is correct. Who was speaking there a moment ago?
Aaliyah, George?
Okay, thank you, Aaliyah. Okay, yes, that's correct. Now, let's change this. I'm going to do a save as, and I'm going to change this to OR. So that's what I'm going to do. And I'm going to have a 2-input OR truth table. So in this case, let's delete all the outcomes. What should we expect for OR? Anyone?
Unless all of the inputs are 0, you would expect the output of 1.
Yes. If A is 1, or B is 1, or C is 1, or D is 1, or F is 1, it just takes 1. That is correct. And who was speaking then?
Michaela Todman.
Thank you, Michaela. Okay, so Michaela, if you would do us the honors, what am I going to enter for the inputs?
0 for that one. 1, 1, and 1.
Correct. Any questions? So let's look at the 3-input table. Same kind of pattern here. Notice the first half of inputs on the first input are 0s. The first half of the inputs are 1s. As you move to the right with other columns, you start to alternate more frequently. In this case, 2 0s, 2 1s, 2 0s, 2 1s, right? And the third column, 0 1 0 1 0 1. And you see the same output holds true for 3 inputs. So if we go from 2 to 3 to 4 to 5 to 6 to 7 to 8 to 16 to 32 to 64, same thing holds true. Also, in like fashion, for the OR, I'm going to do a save as. I'm going to save this as an OR truth table with 3 inputs, which are labeled A, B, and C. We're going to change this, and in like fashion, unless all inputs are 0, everything else, if there's a single 1 showing, the same pattern occurs. So I have a 0 in the first, for the first entry, but then I have 1, 1, 1, 1, 1, 1, 1. Any questions? Now, what happens if we start to mix it up? If we combine the 3 basic, the main topic for today is when we start mixing this up and start combining our basic logic gates or Boolean operators and or and not, how do we work a truth table? And what I want to do is use a case where we start with 2 inputs. And let's open up our study guide. And I think we have a perfect example in our study guide of a 2-function, actually I'm looking for, yeah, that's actually more, that's a little more complex. So we'll get back to that. And that's a 3-input function as well. I'm looking for a 2-input function. I think there was one in our module 1 logic gate. I mean, our module 1 study guide. So give me a second here. Or there may be one in the textbook. So I think it's in the textbook. What I wanted to do was to try a simple example first. So let's go to the textbook. And let's find a basic 2-input scenario with more than one Boolean operator or logic gate in the mix. Okay. So there we go. Oh my. Yeah, I don't want mux yet. I think I went too far. All right. It looks like a lot of the stuff in our textbook and in our study guide is more complex than an initial example would help. So let's just create a new one, okay? And I'm gonna get back to where's my not thing? Indicates not. All right, almost there. Everybody with me?
Yes.
Yeah, that's not showing a not B. So let me see if I can pull this in the actual Word document. All right. Let's create a function, shall we? And I just pressed Control Z. So if I try to use a lowercase italicized F, and then it wants to capitalize it because it's the start of a new line. You just press Control Z. I have a simple function with two inputs, A and B, and it's equal to A or not B. Does everybody see my screen?
Yes.
Yeah.
Okay. I appreciate your patience over the last 2 or 3 minutes. I really thought there was one combination a combination of Boolean operators involving just two inputs. I really thought that there was one readily available in the study guide and in the textbook. I think I'm going to end up revising the study guide for this module so that we have this as a part of the record, right? And to include this primary example. And the reason that this example is so critically important is because I want to walk you through how you use the truth table to discern the outputs that result. We have two inputs, but we have more than one Boolean operator coming. If we just had an A and B, we've already done that. We already did an A and B with an OR in between, right? And I want you to notice that this truth table template states, replace the labels for input 1 with the actual variables specified by the Boolean function, right, provided, or complex logic gate, right? So if you have two or more different logic gates and you have two or more inputs in the mix, you start to get a little complex. And I want to give you a method to use to follow along with this truth table to resolve the output, right? So that's the goal today, is to be able to combine these things. And that's one of our student learning objectives. Any questions so far? So I'm going to go ahead and put A here, and I'm going to put not B here. Does everybody understand? Now, another way to express not B is to say B bar. Everyone, B bar.
B bar.
B bar, right? And so what you can do for output to represent the output is do something like this. You can do something like this. So remembering our order of operations, which Boolean operator or logic gate do we need to engage first? Whether we're talking about software or hardware, either way, what are we dealing with? What do we need to consider first? Are we dealing with the or are we dealing with the not first? Does anyone recall? Well,
is it not?
It is the not. Yes, the not is a wild card. We've said this, but one of the most important things to remember about not is that it typically must execute before anything else, unless it is explicitly stated with parentheses to do otherwise, like after the fact, right? So not is going to apply to be. And here's part of the dynamic we have. We have a truth table we need to populate with all of the possible combinations. So I'm going to put, the first thing I'm going to do is start with my default values, right? I don't want to confuse anyone. So I'm going to go ahead and set this up first. So this is the same possible combinations that can be fed into the A or the B bar, the not B, okay? Now, in order to accommodate, if we were just ORing these, we could look and we could say, okay, if A is 1 or B is 1, but we can't do that. What we have to do is indicate in some fashion what happens after the not executes here. So there are two methods to do this. And I want to show you each method, and I want you to take up one method or the other. Okay? So I'm going to go ahead and put a 1 here. And why am I putting a 1 here? And I'm going to strike through the 0. Why am I going to strike through the 0?
Because the value flipped.
Because the value flipped. Thank you so much. You're brave. I think there's a Disney movie that they made about you. Yeah. Okay. I don't know if you've seen that movie Brave, but it's a pretty interesting movie. Now I'm also highlighting in bold, and I might even highlight with yellow, right? Now, the thing to remember though, and this is really important when it comes to canonical expressions, and this becomes a tumbling point or a stumbling point, you have to note the original input values. You must. You cannot simply erase them and then represent the new ones. It's kind of like, okay, I'm going to do something in my head when I'm in algebra and I'm not going to show my work, but then somewhere along the line I made a mistake and I don't know what happened. You must always preserve the original input so that you can check to make sure that your original table is set up, okay? Now, this is one method to do so, right? So I'm gonna go ahead and finish this up. I'm gonna put a 1 here, and then I'm gonna put a what here? 0 here, right? I'll make this bold and that bold, and I'll copy the formatting here because I just want to do this. Keep it simple. And now I am free to OR this value and this value, then this value and this value. Because now that I have applied the not has taken effect. The B has left the building, and now we're dealing with B bar. Everybody understand what I'm saying? Elvis has left the building.
Yep.
Okay.
Yeah.
So now if A or B bar is 1, what's my output here?
1.
1. Help me out. Next one.
1.
0.
Oh,
Oh, yeah. 0, 0.
oh, I'm glad that happened. It was 1, but when B bar took effect, we have 2 zeros, right? So our output is 0. Everybody see what happened there?
Yes.
Okay, and what do we have now?
1.
1.
1, and what do we have now?
1.
1. Excellent. So this is the truth table that represents a function with A and B inputs where A is ORed with B bar. Okay? And I want you to notice how I articulated, how I expressed that, how I read that function. That's the same thing you need to be able to do. You need to be able to practice reading functions just as I did so that, well, it's considered good form, right? And you don't want to be considered a stepchild for like computer architecture. You want to see something like that and go, oh, yeah, I know what that is. It's a function with A and B inputs where A is ORed with B bar. And then future employers like Intel and AMD will be thoroughly impressed, okay? Now, what's the other option? Well, there is another option, and it's pretty interesting. You don't have to do this. You don't have to use this approach. I'm going to start over again and show you option 2 for how you can manage this. So these are the original values. Oops, I'm sorry. We'll fix that. Let's start over again. What is the alternate approach to accommodate 2 or more Boolean operators or logic gates in combination with only 2 inputs? Well, I'm going to do this. Everybody see my little arrow? How I'm moving my mouse carefully? Yeah?
Yeah.
Yes.
Okay, so what I'm going to do is I'm going to go to my design view. Nope. I'm going to go to my table design view. No, where is it? Where is it? I'm going to highlight the table and then I'm going to right click it. And, oh, come on. I know they didn't move this. Oh, there it is. There it is. Insert. Everybody see this?
Yes.
Okay, it's a table. I'm going to insert to the left. I'm going to insert a column to the left. Everybody see what I did?
Yes.
Yes.
Okay. It's an intermediate step. Okay. So what am I saying? I can copy this over here. Oh, no. Yeah, let me get rid of that extra. I'm going to delete that row. I don't want an extra one. I'm going to insert an extra column, but instead of having B bar here, I'm just going to have B. And so here I have my original AB inputs. Everybody with me? Here I have my original AB.
Yes.
And then I know that I have to do something extra with the not first. So I'm going to not these, and I'm going to put the reverse of 0, which is 1, the reverse of 1, which is what? 0.
0.
1, and this is 0. And then I'm going to do something like this. That way, I preserve my original input values. Again, it's really important to indicate your original input values. If you lose the original input values as you formulate your canonical expression for this Boolean function, you're not going to be able to, you're going to miss things, right? So it's either going to show here or it's going to show in a fashion like this. Now I can OR the 0 and the 1, the 0 and the 0, the 1 and the 1, and the 1 and the 0. And I get clean results here with my final output. Okay. Are there any questions about either of these two methods for taking an extra step with a truth table?
Nope.
Okay. Now that's critically important to understand. Now let's talk about canonical. There's a short term, there's a way to represent the behavior of a function like A or B bar. So I have a Boolean function with A and B inputs, and it is A or B bar. How do I represent this behavior in a shorthand notation? Well, I could include the truth table every time, but that's kind of tedious. So mathematics subject matter experts many, many years ago decided to create this language. It's a way to express Boolean functions, and we call that a canonical expression. And all you're doing is list inputs for each case, a true or one outcome results. Okay? What's the reverse? There is a reverse canonical expression. You list, I'm going to put variable inputs here, okay? Original variable has to be original, hence the reason for including the original values, right? Because otherwise it gets really bad. List original variable inputs for each case a false or zero outcome results. Now, I'm going to say this explicitly. Which one would involve a shorter expression, stating the true cases or the zero cases?
The zeros.
The zero cases, right? I mean, wouldn't it be nice if you could just indicate one set of inputs that provide a false and what else do you know? Else A or B bar is true. In the terms of the pseudocode for a programming statement, or in terms of the architecture of a logic gate you construct, and you have many choices to build different complex logic gates, right? There are times you want the most efficient, the quickest result that achieves the outcome with the least effort. And there are times where you don't, and we'll explain that in just a minute. There are times where you intentionally kind of go around your elbow to get your ears so that you sort of muddy. Has anyone ever heard of like fuzzy logic or a case where you have to have delays for a given measurement and response? Well, all right, so let's give you a quick example. Did you know that some fire suppression systems suck the oxygen out of a room? If a fire alarm hits, do you want that to execute immediately while live personnel are in the room and the doors lock and the fire suppression system executes? Or do you want there to be a delay so that people can get out?
You'd want a delay.
You'd want a delay. And why am I telling you this? Believe it or not, there have been actual cases where a fire suppression system has executed, the doors have been locked, it has expressed noxious gas to extinguish the flames, and unfortunately, it also extinguished the workers. It's happened, okay? Yeah, yep, not good. All right, so here's the thing to remember. You need to intentionally select which expression method, either the standard canonical expression or the reverse. So when we say standard, we mean the normal one, right? We're talking about the case. And then when we say the reverse canonical expression, you're listing variable inputs for each case. Now I'm going to add a little description here. Note, for each original input that is false or zero, use a tick, which is a single apostrophe, to indicate, all right? I'm going to say the same thing down here, right? Now that's, so the first thing we're concerned with is looking at the outcomes and saying, do I have more trues or more falses? Do I have more ones or more zeros? And I'm going to make a decision based on that, and our class made the correct decision, right? Thanks to the powers of observation of one of your classmates. It's like, okay, if I write out expressions using the standard canonical expressions, I have to make 3 different statements about cases where it's true. But if I choose to use the reversed canonical expression, I really only have to worry about one case, and I'm going to look at the original input values, not after the bar has done its magic. Let's repeat that again. I'm looking at the original input values, not the one after bar has been executed. Everybody understand that?
Yes.
Yes.
So
Yes.
so I have an input here for A and it is false. So in this case, I'm going to say I have a function, right? And I'm going to do my Control Z to make sure it stays that lowercase with A and B. And the canonical expression is, so I'm going to do this. I'm going to say A tick B. Whenever I see a tick, does everybody understand what I just did there? I'm going to make this bold. I'm actually going to put a slight space there. So that's a reverse canonical expression. Yeah. That's a reverse canonical expression, and this is a standard canonical expression, right? What happens if we change it? Let's take a different case. I mean, right, so let's say that we had to do the, let's say we did the standard canonical expression. All right, let's pretend that we're crazy and we just like to do a lot more writing with a shorthand format because we're crazy enough to defeat the whole purpose of a shorthand format, right? And I want to show my intellectual prowess by stating each of the true cases, right? So what do we have here? What's my first expression for these inputs that result in a true output? What would I put here? A tick.
Would you say
Go ahead.
A tick, B tick?
B tick is what I'd say. And then I'm going to do this. I'm going to put an OR operator in between because I have three different cases. If I want a true from this Boolean function, I have to have A tick, B tick, or A B tick, and notice I'm putting some extra spaces in there, right? Why am I putting extra spaces in there? Well, it just makes it easier to read when you're dealing with the combinations, right? What's the last case? Are there any ticks in the last expression?
No.
No, it's just AB.
No.
So which one involves the shorthand? The simple, easy way to describe the behavior of the entire function? Well, we know that for a reverse canonical expression, we're talking about things that are false, else everything else, all other inputs are true, right? So when we're doing the logic, we're just going to define that one case that's this, else, everything else, right? In those logic statements. And you'll see what I mean about the logic statements in a minute. The pseudocode logic statements. Any questions about what we've demonstrated here? I'm going to reverse this and make it an and. Okay. So I'm going to save this as a 2-input complex table. I'll call that example 1. Now, what do I need to do to make this a totally different table? Well, I can put the dot in there, right? So I can use the dot, and that's in here somewhere. Pretty sure. There it is. Everybody see my dot?
Yeah.
Okay, so I'm going to put that in here. My truth table, dot. And I'm going to do it here, dot. All right. And is this part of the truth table different?
No.
No,
No.
it isn't. What about this part of the truth table? Is that different?
No.
No.
No, it's not. It's just this part. So what am I saying? I'm going to have a different outcome now. So I know that a 1 and 0 when I'm ANDing or multiplying, what's my value here?
Zero.
Zero.
0. Yeah, what about the next one?
Zero.
What
Zero.
about the next one?
One.
1.
1. And what about the next one?
0.
Zero.
Yeah, I can do the same thing here, right? If I use this table, I get the same result, 0, 0, 1, 0. I get a uniquely different result. And are my canonicals the same? Which would I prefer to use for economy of expression this time? Would I use a standard canonical or a reverse canonical?
Standard.
A standard, because I only have one case where it's true and every other case is false, else false. When I'm writing out pseudocode, when I'm writing programming code, I can say, if so-and-so, then 1, else false, right? So, and we're going to talk about that in just a minute. Okay, so I'm going to take the standard expression and now I'm going to do different. What do I do this time? If what? How do I rate that in canonical terms? That's the only case that's true.
A, B, tick.
A, B, tick. I already have it. From my previous example, I already have that, right? Now, what about this one down here? It's false if I have A tick, B tick. It's false if I have what?
A tick.
A, B, what? A tick B, right? Everybody see that?
Yeah.
Yeah.
And AB. Now, isn't that weird? It's like, okay, I have a true input and I have a true input, but now I have a false output because I have one not in the mix, right? That's what we mean by wildcard. It's like, oh, if I put that not in just the right place, I can bung up I can completely reverse this thing, okay? So let's make sure we get this down. It's a 0, and a 0 if it's A tick, B tick, AB tick, or AB. A tick, B tick, or what was the other case? AB tick, or
A tick, B tick.
AB.
A, B.
AB.
The second one should be A, tick, B.
The second one should be A tick B. That is correct. It's easy to get flipped. It's easy to get turned around. So you want to double check. Good catch. Thank you. A tick, B tick. A tick B. Did I state A tick B the first? I stated it, but I didn't write it that way. Is that the problem?
I think I stated it, but then you corrected me, I think.
Yeah. And then AB, right? And this is the case where AB tick is where you get a true. Okay, so we conclude our class session having reviewed how best to use a truth table to resolve a Boolean function that has 2 or more Boolean operators in the mix. And we took the simple case where we had 2 inputs. On Wednesday, we cover 3 and 4 inputs. And we talk about logical expressions that can be built with pseudocode before you go into the HDL environment. So what am I saying? The canonical expression becomes most valued because it helps you understand the most efficient approach, requiring the least number of components. And when you state the logic, you also gain another view of a design principle. And you want to do this before you go into the HDL simulation environment and build your hardware components, okay? That's where we'll leave off, and we'll cover, now I may ask you at the start of class on Tuesday to resolve a simple 2-input function with more than one Boolean operator, okay? And I may give people additional credit if they get it correct. So what am I saying? You go into Blackboard, you have 3 minutes. I post it at the beginning of the class. Everybody has their 2-input truth tables ready because those are in your resources folder and the templates are already in there, right? And then you practice the example we just walked through. So be ready for that on Wednesday. Any questions before we close for the day?
No question.
All right. Well, thank you for joining us, and my compliments to each of you who were very much on point with detail along the way. Well done.